Okay, I'm going to be working on number 16 from 8.5, I believe it was, or 8.6, I'm sorry. The problem was f of x equals x squared arctangent of x cubed. All right, so what we want to do is we want to write this, find a power series representation of the function. So this definitely doesn't have the 1 over 1 minus u that we've been using. So maybe I can recognize that one of these is somehow connected to this. So just remember, before I get to this problem, the following. That if we had arctangent, excuse me, of x, that this is equal to the integral, or the antiderivative, of 1 over 1 plus x squared dx. So that's something we know from earlier in the semester. And this right here can be rewritten as 1 over 1 minus negative x squared dx, like that. And this right here does have the form of 1 over 1 minus u, where u for us here would be negative x squared. So with that said, I should be able to rewrite this as, not this, I'm not working with this right now, just this. This is the integral of the sum n equals 0 to infinity of negative x squared to the n. And then what I can do is clean that up, the summation, peel things apart. Forgot my dx here. N equals 0 to infinity. I've got negative 1 to the n, and I have x squared to the n, which I'm going to write x to the 2n dx. So at this point, I can use several things to figure out, what the antiderivative of this is. I can use the rule for antiderivatives of a series, and I can just do, all right, no more integral. This is equal to some constant plus a new sum. N is still going to start at 0 and go to infinity. Negative 1 to the n doesn't change. But then, be very careful. I have to add 1 to this power and divide through that. So it's by that. So it's going to be 2n plus 1 x to the 2n plus 1. So because we have a 2n up here, we have to pay a little bit of attention to this part. So remember, if we took the derivative, the power would come down. That would cancel. We'd reduce the power by 1, and we would get that. Now, I'm going to show you a slightly different way to do that same exact step. That's I don't know if it's easier, but it's a little safer. What I'd like to do is I'd like to take this right here, and I'm going to write out the first few terms of this. So if n is 0, we get a 1 here, we get a 1 here, so we get 1. If n is 1, we get minus, and then we get x squared. And then plus would be the next one, and then n is now 2, so x to the 4th, and then minus x to the 6th, then plus x to the 8th, minus x to the 10th, plus dot, 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 and we're integrating all of that, right? Now if we integrate that, let's integrate these term by term. This will be x, and this will be minus 1/3 x cubed, plus 1/4 x to the 4th. I'm sorry, 1/5 x to the 5th. And then minus 1/7 x to the 7th, plus 1/9 x to the 9th, minus 1/11 x to the 11th, plus dot, dot, dot. And then, of course, there's a c at the end of all of that. So this should give you that same answer, but let's act like we don't know that. Let's try and rewrite this in sigma notation. So what we notice is that it's an alternating series, right? And it starts with a positive. So I'm going to go negative 1 to the n. I'm going to start n at 0. Okay, go to infinity. So that should give me an alternating series starting with the positive. And then notice that this is x to the first power, this is 1 over 1. So when I plug in 0, I need to get a 1 and a 1. When I plug in 1, I need to get a 3 and a 3. When I plug in 2, I need to get a 5. Oh, I forgot to put 5 here. 5 and a 5. So these are odd numbers. So I need to create the odd numbers starting with 1, but n is going to start at 0. So what I'm going to do is 1 over, here's how I create the odds, 2n, and then plus 1. So if I let n be 0, I get 1. If I let n be 1, I get 3. n be 2, I get 5. And then the power will be the same thing, 2n plus 1. And that matches over here, you can see. So there are two different ways to get to this. So let's remember that. If the final result is this, that tangent inverse of x is equal to the integral of this thing, which we said is equal to this. Sum n equals 0 to infinity, negative 1 to the n times 1 over 2n plus 1, and then x to the 2n plus 1, plus a constant. Now we can actually figure out what that constant is if we just use the fact that if we plug in 0, our tangent of 0 is equal to, well, if all these x's are zeros, then this whole sum is 0, and so we have just plus c. And our tangent of 0, if you just go back to pre-cal, that's 0. So c is 0. So really, we know that this constant is 0. So that is how we can rewrite our tangent of x as this power series. Now let's go back to the original problem. F of x equals x squared times, now tangent of x cubed. What I'm going to do is I'm going to take x cubed here, replace this right here with x cubed, which in this formula would replace this x with x cubed right there. And so what we get is sum n equals 0 to infinity, negative 1 to the n, 1 over 2n plus 1. And then this, when I multiply the 3 times this, I get x to the, 6n plus 3. So 3 times that, 3 times that. So that's what f of x is. Now just move the x squared inside. So when we move the x squared inside, we get sum n equals 0 to infinity of negative 1 to the n times 1 over 2n plus 1. And then times, when we put an x squared out here, we add the exponents, so we get x to the 6n plus 5. All right, so that should be your power series. All right, now you have to find the radius of convergence, so all you have to do is take this right here, absolute value of that less than 1. So I'll let you do that yourself. All right. Let's look at number, what is it, 17? 17. F of x is x over 1 plus 4x, that quantity squared. So if I take that x on the outside and rewrite this like this, I know that I can somehow get this right here to be something like 1 over 1 minus u, because I can look at that as being 1 minus negative 4x. But the squared causes a problem. So let me see if I can somehow connect can I connect this to just this somehow? Well, I'm pretty sure that if you take the derivative of this, you're going to get something close to that. Let's see. What would happen if I take the derivative with respect to x of this? So that's the same as the derivative with respect to x of 1 plus 4x to the negative 1. I'm just bringing it up, the whole thing. And then I use chain rule. So negative 1 comes out. And then it's 1 plus 4x to the negative 2 times 4, because you have to take derivative of what's inside. So this is equal to negative 4 times 1 plus 4x to the negative 2, which is the same as negative 4 over 1 plus 4x squared. So you can see that the derivative of this is almost that. Okay, I mean, sorry, the derivative of this is this, which is almost that. So watch what I'll do here. The only difference between this and this is the negative 4. So if I come back and I say now, take negative 1/4 times the derivative of 1 over 1 plus 4x. That will be equal to, so here's the derivative of this is this, and I'm putting a negative 1/4 in front of it intentionally because I know that that's going to turn out to be negative 4 over 1 plus 4x squared, and then these go away and you're left with 1 over 1 plus 4x squared. All right, this is a good thing. All right, this right here is this. I can rewrite this as a power series, and I can differentiate a power series. So now let me come back up here. So f of x is equal to the x we had in front times this, right, which is this. So negative 1/4 times the derivative with respect to x of 1 over 1 plus 4x. That's my original function. And now I'm going to rewrite this with the power series. Let's go ahead and just do it right here. Remember that the plus is the same as minus negative 4x, like that. And so we get negative 1/4 x, I'm just putting those two together, times the derivative with respect to x of the power series, n equals 0 to infinity, of negative 4x to the n. Now there's a radius of convergence that we'd have to worry about, but I'm leaving that to you. You just have to let that absolute value of that be less than 1. So now how do we differentiate this? Well, we first have to peel it apart. So we have to take that negative 1/4 x times derivative with respect to x of sum n equals 0 to infinity of negative 1 to the n times 4 to the n times x to the n. And remember that this piece right here is our c sub n, and then right here, this is our x minus a to the n. So we're ready for the derivative now. And the way the derivative works, the n is going to come down, we're going to subtract 1, the index is going to go up by 1. So we have negative 1/4 x times, no more derivative, n equals 1, because I'm shifting it, because that's what you do when you take the derivative. C sub n does not change, and n comes out, and subtract 1. And then what I'll do is I'll bring, let's see, how should I do this? I'll bring the negative 1/4 in, and well, you know what? Yeah, I'll bring it in, and I'll bring the x in. So let me do that over here. So that is equal to sum n equals 1 to infinity. And then when the x comes in and goes next to this x, I add the exponents, I get just x to the n on the outside. And I have an n in front of it. And then I have, let's see, how do I want to do this? How about we look at this negative in front of the 1/4 as a -1? And that way when I take this -1 and put it times this -1 to the n, I add the exponents, I get -1 to the n plus 1. And then I get, I need a little more room here, 1/4 times 4 to the n times x to the n, that's where I am. And look at this right here, these two. That's the same as 4 to the n over 4 to the 1, which is 4 to the n minus 1. So I'll go one more line. Sum n equals 1 to infinity, -1 to the n plus 1, and then I have 4 to the n minus 1, and then I have x to the n. All right, and let's see if that's what they kept there. All right, that's fine, but they do go and they do switch this index back to 0, which you wouldn't have to do, but let me just do it just to show you that our answer matches the back of the book. So what I'm going to do is try and make this a 0 down here. So I need to put n plus 1 over here so that when I subtract 1 on both sides, I'll get 0. So I'm going to let all my n's turn into n plus 1's. So I get sum n plus 1 equals 1 to infinity, -1 to the n plus 1 plus 1, and then 4 to the n plus 1 minus 1, then x to the n plus 1. So that's replacing all my n's with n plus 1's. Subtract 1 on both sides there. N is 0 to infinity. This right here becomes -1 to the n plus 2, and we saw before that this is the same as -1 to the n times -1 squared. -1 squared is 1, so we don't even care about that. It's just -1 to the n. And then here, this is just going to be 4 to the n, and then here, x to the n plus 1. And that, I believe, should match what they have in the back. I left my n out. Shit. I left my n out. Darn it. Should have caught that earlier. Right here, when I was rewriting this, there was an n from, remember when we did the differentiation, the derivative. So there should have been an n right here, which meant that there should have been an n, which we replaced with n plus 1 right there. And so next to this somewhere, n plus 1. Sorry about that. All right. That's it. Let's look at 18. F of x equals x over 2 minus x cubed. I feel like I did this in class, but I'm just going to work through it. So I realize I can just split this up, 2 fractions. And I can peel that x cubed off and look at this. And I'm realizing that 2 minus x, I can probably get that to look like 1 minus u. But the cubed causes a problem. So I think that this is the derivative of something, though. If I take the derivative, let's see how close we'll be here. Well, you know what? Let's do it a different way. Instead of guessing what that's the derivative of, let's try a little different. Let's integrate this. So if we integrate 1 over 2 minus x cubed dx, we do a quick u substitution. U is 2 minus x. Du is negative dx. Then this integral becomes -1 over u cubed du. So I'll let you go through your own work to verify that. That's integral negative u to the -3 du. And then using the power rule, we add 1 to this, which gives us negative 2. We have to divide by it. So when we divide negative 1 by negative 2, we get 1/2 u to the negative 2 plus a constant. So derivative of this comes out, turns into a negative 1, got it, u to the negative 3. So that should be it. Yeah, so this is equal to 1 over 2 times 2 minus x squared. That's what that is. So we can't, I want to verify that when we take derivative of this, well, I guess we're okay with all this work, I guess, because we've done it so many times before in the semester. This right here is not this, right? I'm sorry, is not something I can work with. I started with this, I integrated once, I was hoping I could do a power series on that. I can't. So if I integrate that one more time, I should be able to get back to something I can do a power series of. So let me try and integrate now this. So that 1/2 I'm going to pull out, you get 1 over 2 minus x squared dx. So I'm going through the same thing again. I'm doing a second integration. I'm using the same substitution. And when I do that, I have 1/2 integral. When I rewrite this, this is going to be negative 1 over u squared du, which is 1/2 times the integral of negative u to the negative 2 du. And then when I actually apply the power rule, I get 1/2. Let's see, I need to do add 1 to this, which gives me negative 1. Divide through by it, so that should just be positive 1, u to the negative 1, which is just 1 over 2u, which is just 1 over 2 times 2 minus x. Okay, so what in the world does this all mean? It means that if we take this expression and we differentiate it twice, we should get this. So if we take that expression, differentiate it twice, we should get that. That is something I can do a power series of. So let me just check that what we've done is right. I'm just going to look real quick. I'm going to take this right here. I'm going to take the derivative with respect to x twice, the derivative with respect to x again of 1 over 2 times 2 minus x. So if I do this 2 times, I should get that back exactly. Not that, but just this. So I'm going to rewrite it like this, so it's easier to differentiate. Okay, that's the original one. So let me do this first derivative. I'll still have another derivative we're going to take. But negative 1 comes out, that's negative 1/2, 2 minus x to the negative 2. Then the derivative of what's inside, which is negative 1. When I put this negative 1 and the half together, it just becomes positive 1/2. Now do the derivative again. So when I do derivative again, negative 2 comes out, that's going to be negative 1, 2 minus x to the negative 3 this time, times derivative of what's inside, which is negative 1. These two negative 1s come together to be 1. This is 2 minus x to negative 3, and that is this. So let me see if I can write this out now to make any sense at all. If I rewrite this, I have x cubed times this, which is this right here. So it's the derivative of this, which is, let me write it this way, 1/2 times 1 over 2 minus x. All right, so I just split that apart. The reason I did that is because I'm about to rewrite this using a power series using this thing. But I've got to make it look like that first. So how about we rewrite this x cubed times the derivative with respect to x of the derivative with respect to x of 1 over 4. So I pulled a 2 out of this and popped it out here with this 2. And when I pulled the 2 out, I would have been left with a 1 minus 1/2 x, like that. And now for this piece, I can do a power series. So this is equal to x cubed times the derivative with respect to x of the derivative with respect to x of, let's see, 1/4 is this. And now this is a power series. Sum n equals 0 to infinity of, not negative 1/2, positive 1/2 x to the n. All right, so what do we get here? We get x cubed times the derivative with respect to x of the derivative with respect to x of, let's see, 1/4. How about this 1/4, since it's a constant? Why don't we just pull it out? Because the derivative won't affect it. It'll come out and come out. Why don't we just put the 1/4 on the front? And then in here, we have sum n equals 0 to infinity of 1/2 to the n, x to the n. And that's it. It's peeled apart. It's ready for the derivative. So now I'm going to take that derivative. So I have 1/4 x cubed times the derivative with respect to x of, now let me take this derivative. So I have sum, the index is going to come up, n equals 1 to infinity, and then this stays, and then the n comes out, and n minus 1. All right, so there we go. Now, if we're going to do this derivative a second time, what I'm going to need to do is get this thing to be x to the n, not x to the n minus 1. So I need to do a quick switch here. If I want to make that x to the n, I need to replace all my n's with n plus 1s. So if I do that, I'll let you do that on your own. If I replace that with n plus 1, this sum will now start at 0. Go to infinity. It's be 1/2 to the n plus 1. Then it'll be n plus 1 here. And then x to the, when we do that, we get n. And now we can do the derivative again because this is x to the n. And I'm going to get 1/4 x cubed times, no more derivative, sum, index is going to come up by 1 to infinity. And then I have the 1/2 to the n plus 1 doesn't change. The n plus 1 doesn't change. But here the n comes out, then x to the n minus 1. The last thing I'm going to do is, well, I see some stuff I can do with that 1/4. All right, let's push this through now. All right, x cubed is going to go on the end of this, and I'm going to add the exponents. So I'm going to have sum n equals 1 to infinity. At the very end, I'm going to have x to the n plus 2, because when I put x cubed here and add the exponents, I get that. N plus 1 is not going to change. I'll put the n in front of the n plus 1. I'll just switch the order. This is the part that I thought was a little bit tricky. The 1/4 comes in. So I'm going to rewrite 1/4 as 1 over 2 squared. And then, well, you could even write it this way. 1/2 squared, right? That's 1/4. And then this is 1/2 to the n plus 1. And when you add these two together, right, the two exponents, you should get 1/2 to the n plus 3. So sum n equals 1 to infinity, 1/2 to the n plus 3 times n plus 1 times x to the n plus 2. And I'm wondering if they left it like that. They went with an index back, they took their index back to 0. So if I'm going to match the book, I'm going to have to let n turn into n plus 1 and then rewrite it. So let's do that. So this sum, if that's n plus 1, and do the little subtraction, n is 0. Everything's replaced with n plus 1. 1/2, that's n plus 1, so it's n plus 4. And then this is n plus 1. This is n plus 1 is n plus 2. And then this is n plus 1 plus 2, which is x to the n plus 3. And that should match what they have. Yeah, they have it written a little different, but I think if you look at the answer in the back of the book, you can tell. They just put, 1 to any power is 1, and then 2 to that power, they just put it on the bottom. So there's your power series. Okay. How are we doing? We got 15 minutes. Number 19. Let's see how quickly I can do 19. Ooh, I can't do 19 quickly. Well, no. I don't think I have enough time to do 19 and 20, so I'll have to do another video to do 19 and 20.